Imagine a world where the ground beneath your feet suddenly begins to dance. Not a gentle sway, but a violent, unpredictable tremor. Some buildings stand tall, defiant against the chaos, while others crumble into dust, their steel and concrete twisting into grotesque shapes. What invisible force decides their fate? Why does one skyscraper survive unscathed, while its neighbor collapses? The answer lies in a hidden secret, a fundamental principle of physics that governs everything from a child's swing to the mightiest structures we build. It's called resonance. At its core, resonance is a simple idea. Every object has a natural frequency, a specific rhythm at which it prefers to vibrate. Push a swing at just the right moment, at its natural frequency, and it will soar higher and higher with minimal effort. Push it at the wrong time, and it barely moves. Buildings are no different. Each structure, whether a small house or a towering skyscraper, possesses its own unique natural frequency. This frequency is determined by its height, its stiffness, its mass, and the materials used in its construction. Taller, more flexible buildings tend to have lower natural frequencies, meaning they sway more slowly. Shorter, stiffer buildings have higher natural frequencies, vibrating more rapidly. Now consider an earthquake. When the Earth's tectonic plates grind past each other, they release immense energy in the form of seismic waves. These waves travel through the ground, causing it to shake. This ground motion isn't just a random jiggle, it has its own dominant frequencies. A rhythm dictated by the earthquake's magnitude, the type of soil, and the distance from the epicenter. The danger arises when the frequency of the earthquake's ground motion matches the natural frequency of a building. This is resonance in action. The building begins to absorb more and more energy from the shaking ground, amplifying its oscillations. Each tremor pushes the structure further, much like repeatedly pushing a swing at its peak. The results can be catastrophic. The building's movements become exaggerated, far beyond what its design might normally withstand. Columns buckle, beams fracture, and connections fail, leading to structural collapse. This isn't just theoretical. History is filled with tragic examples. Take the 1985 Mexico City earthquake. The city sits on ancient lakebeds, which amplified certain frequencies of seismic waves. Many buildings between 6 and 15 stories tall, whose natural frequencies matched these amplified ground motions, suffered disproportionately severe damage or complete collapse, even those far from the epicenter. Shorter and much taller buildings with different natural frequencies often fared better. Engineers and architects are acutely aware of this invisible dance. Their challenge is to design structures that can withstand the unpredictable rhythms of an earthquake. They employ sophisticated techniques to either shift a building's natural frequency away from common earthquake frequencies, or to dissipate the energy that resonance would otherwise amplify. One ingenious solution is base isolation. Imagine placing a building on giant flexible bearings, like rubber pads or sliding mechanisms. These isolators decouple the building from the ground's motion. When the earth shakes, the isolators absorb much of the energy, allowing the building above to move much less violently or at a different, safer frequency. Another strategy involves tuned mass dampers. These are massive weights, often hundreds of tons, installed near the top of skyscrapers. They are designed to oscillate out of phase with the building's natural sway, effectively counteracting and dampening its motion. It's like a giant pendulum absorbing the building's energy, preventing it from reaching destructive resonance. Even the materials themselves play a crucial role. Modern construction uses ductile materials, like certain types of steel, that can deform significantly without fracturing. This allows buildings to sway and absorb energy rather than breaking catastrophically. The goal is not necessarily to prevent all damage, but to prevent sudden, life-threatening collapse. The big reveal is that our cities are not static monuments. They are dynamic entities, constantly engaged in a silent, intricate dialogue with the forces of nature. Every skyscraper, every bridge, every home is a carefully orchestrated symphony of materials and physics, designed to harmonize with the Earth's rhythms or bravely resist them. The next time you look at a building, remember its hidden secret. Remember the invisible dance it performs with the ground beneath. For in that silent conversation lies the difference between standing tall and falling to dust, a testament to human ingenuity in the face of nature's raw power.